Hello, Calculus BC Explorers. We're back on our second day of a deep dive into a specific type of polar graph. Last class we looked at polar graphs that made rose petals, and although we went through a lot into how to create that graph, ultimately at the end, if you were just able to find the interval that made one loop, you'll be just fine and dandy for when we get to the area, because oftentimes they ask you for the area of just one petal, I guess, instead of a loop, and you need to know how to isolate that one petal. Of course, the majority was spent on how polar graphs are created and what happens when you have negative r values, and that will come into play today. So let's begin. Given the equation r equals 1 plus 2 cosine of theta, take a quick second and decide, or write down, what do you expect this graph to look like, and what's it called? Ready, set, go. Well, hopefully you already know what it's called because you looked at the title. We can be a little bit more specific. This general format, when you have r equals a plus b times, I'm just going to call it a trig function of theta, though really it's sine or cosine. This is always of the style of a limaçon. Right there. And I was just sharing with my wife. I was like, oh, I wonder what the difference is between limaçon and escargot, because they both mean snail in French. And a limaçon is usually an inedible snail, versus escargot is, not shockingly, an edible snail. That's why you see escargot on menus and not limaçons. So there you go. Random side story. And we also learned last class, if A is smaller than B, right? If A is less than B, like we are up here, then this will create a limaçon with an inner loop. Additionally, because there's cosine here, I would expect the bulk of the graph to be on the positive side of the x-axis with some sort of inner loop over here. Easy enough. Part B, tables again. Uh-oh. This one's going to go faster than the other, though, I promise. Fill in only the top table with the 4 given values of theta, and then we're just going to graph that part. So, top of the table, we have 1 plus 2 cosine of theta, so 1 plus 2 cosine of 0. Now that we've done that, we're going to zoom in. This becomes 1 plus, let's see, cosine of 0 is 1, 1 plus 2 is 3. Nice. All right, pi over 3, 1 plus 2. Notice that I picked pi over 3 instead of pi over 6 here. Why would I have done that? Oh, because pi over 3, when you apply cosine to it, becomes 1/2, as opposed to pi over 6, when you do cosine, is root 3 over 2. And I didn't want to introduce any square roots, so we could avoid using a calculator for a while. By the way, you will need a calculator at some point. So half of 2 is 1. 1 plus 1 is 2. Pi over 2, we need to realize that pi over 2 is on the y-axis. Cosine on the y-axis is always 0, and so we end up with 1. And then last but not least, 2 pi over 3. Don't forget that 2 pi over 3 is in the second quadrant. That's where the x-axis is negative, right? Second and third quadrant, so cosine is going to be negative. So this becomes 1 plus 2 times negative 1/2. This is negative 1. 1 minus 1 is 0. And graphing these points, we should be pretty good at this by now. Rotating 0 means we haven't rotated anywhere. We are just right on this x-axis, and we need to go out to a radius of 1, 2, 3. Then we are going to rotate to pi over 3, and hopefully remember this before, where we have our pi over 6, pi over 4, pi over 3, right? These are our thirds right here. Okay. And we're going to go ahead and plot at a rotation of pi over 3, a radius of 2, right here, right? And then we have pi over 2 rotating up here in a radius of 1. And last but not least, 2 pi over 3, that's this guy right here, which is a radius of 0. Now, I'm actually going to go ahead and do a darker line right here, so that we can see where we hit that radius of 0. I always like to put in a line to show where 0 happens. And so how do we create this graph? Well, we started over here, and then remember, this was a radius of 3, then 2, then 1. So this function created a radius of 3, and then we had something smaller, and smaller, and smaller, until we got to 2, and so on and so forth. So there are an infinite number of points here. So we're going to kind of spiral in. We go past pi over 2, so there's a bit over here, because we haven't gotten to 2 pi over 3 yet. But by the time we get to 2 pi over 3, we need to be back to the origin. Great. First part. Without completing the other two tables, how many times will the graph touch the origin on 0 to 2 pi? This again, well, at least we're good at it, and guess what? There is not a multiple angle in here, and so this solution becomes much easier, promise. So as a reminder, if we want to find where this graph touches the origin, we need to set our radius to 0. That's a fancy way of saying at the origin, and then we just get to solve. Okay. As we solve, subtract 1, divide by 2, assume we can do that, and we find that cosine of theta equals -1/2. Don't forget that when you solve trig equations, we don't actually apply inverse cosine to both sides because that will only give us one answer. There are an infinite number of answers here. So we know cosine of theta equals -1/2 is going to occur twice. Everything occurs twice except for -1 and 1 on here, and it's going to occur, well, which quadrants will this occur in? Well, -1/2, cosine being equal to a negative means we know that that has to occur with the negative x-axis, so either in quadrant 2 or 3, which means we can ignore these two. Two triangles it is. One triangle here, and then some sort of other triangle over here. We're going to use -1/2 to build the triangle. If you know your unit circle, you can probably skip all this, by the way. You should just know the answer. Here's going to be one value of theta. We know that this is -1 and this is 2, right? That's from SOHCAHTOA. And then you can either use the Pythagorean theorem, but really you should know that this has to be a 30, 60, 90 triangle, right? There's only two types of triangles you deal with, 45, 45, 90, 30, 60, 90. So we build this guy. And then the last question becomes, what kind of angles do we have here? Well, we know the smallest side, in this case 1, is always across from the 30, which makes our other one angle over here 60. Okay. So that looks pretty good. We also need to remember that 60 is the same as pi over 3. So to get there from the origin, we have to go 2 pi's over 3. Therefore, we have found one answer, that theta, if you do 2 pi over 3, will build a triangle where cosine of that is -1/2. But then we can go further because we should realize that this is 3 pi over 3 down here, right, at the axis. And so we're just going to rotate further around and get all the way over here, and I think that will be 4 pi over 3. There we go. Found our two answers for theta, and that's it. We don't get to those triangles again until you go past 2 pi, so they only asked from 0 to 2 pi, so I think there's only two values here. So as long as you're comfortable with your basic trig values, then that's not too bad at all. Now notice 2 pi over 3 and 4 pi over 3 are right here. 2 pi over 3 was 0, and 4 pi over 3, we might as well fill that in, is also 0. Fill in the second table above. If your answers are not integers, try to approximate the values without using a calculator. Because we're graphing, this is one of the best parts of graphing, you don't need to get perfectly nice numbers, and you don't need to graph them perfectly either. Just ballpark it. Now, if you want a calculator, you can, but I'll do my best without a calculator, and we'll see how we do. 3 pi over 4, we have 1 plus 2 times the cosine of 3 pi over 4. Second quadrant, so we're negative again, so 1 plus 2 times negative root 2 over 2. These cancel, it becomes 1 minus square root of 2. I happen to know that square root of 2 is 1.41 something, so 1 minus 0.41 is going to be like negative 0.41-ish. As long as you knew that square root of 2 is bigger than 1, and you know that that's somewhat negative, you'll be fine. Okay. Pi, 1 plus 2 cosine of pi. Cosine of pi is -1, so that makes this much easier. 1 minus 2 is -1. And 7 pi over 6. I had mentioned before that I didn't use pi over 6's because cosine's not a nice number when we use pi over 6, but I ran out of nice trig values after here, so we had to use it, right? I had to use every value I could before we got over to 4 pi over 3. So 1 plus 2, and then this becomes negative, still negative third quadrant, negative root 3 over 2. These cancel. I don't know what the square root of 3 is, but I know two things. It's smaller than the square root of 4. So 1 minus 2 would be -1. It's not even going to get to -1, but it's bigger than square root of 2. So it's somewhere in between negative 0.41 and -1 for our final answer. I'll just call it, I don't know, negative 0.6, something like that. Doesn't really matter here. Okay, and let's go ahead and graph those points. Now you'll notice that all of the r values are negative here. So from 2 pi over 3 to 4 pi over 3, and we're going to do this like this. So we have from 2 pi over 3 to 4 pi over 3, that's this rotational zone. All of the r values are negative. So if the r values are negative, they are not going to show up in this zone because they are going to flip over to the other section. So what does that mean? Well, if we're at 3 pi over 4, let's put this guy up here, 3 pi over 4, and our answer is negative 0.41, instead of going out, I'll zoom in here, instead of going out 0.41-ish right here, about halfway through, we go out the other way to 7 pi over 4 and put a cute little point. At pi, which is on the axis, right, we have negative 1, so instead of going out 1 towards pi because we're negative, we go the other direction. 7 pi over 6, this radial line, instead of going out 0.6 right here or so, we go out the other way at pi over 6, something like that. And then at 4 pi over 3, we are back to 0. So what does this look like? Well, we started by going out here, then we come around, swing around, and come back to the origin. Look at that, inner loop. How exciting! Now, the nice part is here, we're going to go ahead and fill in this last table, and I'm going to let you guys tackle that one. See if you can be clever about it, maybe use what we did up above to help you fill in a couple points, and then we'll see how you did. Ready, set, go. All right, hopefully we were successful. After 4 pi over 3, I'm pretty sure pi over 2 is always a really easy one to do, right? Or rather 3 pi over 2, apologies. So if we do this in yellow, I'm probably going to choose 3 pi over 2. That's going to get us a nice one. What are some other ones that I have to choose from over here? I don't have too many more, I don't think. We could do, how about a pi over 4, and then, oh yeah, pi's over 3 are pretty nice too. So let's do like a 5 pi over 3. And then, why not? How about 7 pi over 4? We'll have to approximate that one, but it should be fine. And I bet we will be A-OK here. So, yeah, let's rock and roll. 3 pi over 2, 1 plus 2 cosine of 3 pi over 2. That is 0. And then this just becomes 1. So, we're here. Okay, and then 5 pi over 3, 1 plus 2 cosine of 5 pi over 3, is 1 plus 2 times a half. We're positive now that we're in that fourth quadrant. 1 plus 1 is 2. So 5 pi over 3, we're out to 2. I bet you can see what's happening. I don't even need that last piece, right? Couldn't I just go like that? Yeah, I think that's going to look just fine. So we've done well there. Nothing too terrible, and now we can see our limaçon with an inner loop. If you wanted to see that on Desmos, I have it set up so you can see that drawn. I guess this should be 3 over here. Here's Desmos. I have this set up so as I move my slider, it changes theta. Right now, it's only graphed this equation from 0 to 0. So really the only thing that's there is a point, and it won't show that. But as I do more, take a look at what happens. We draw this outer part first, and then rate it 2 pi over 3, if I can get it. There we go, we're back at the origin. And then between 2 pi over 3 and 4 pi over 3, we create this cute little circle here, this inner loop. And then from 4 pi over 3 to 2 pi, we finish this off. If I were to keep going, if I'd go to 4 pi, it would just retrace the graph over and over again. So it completes one full rotation from 0 to 2 pi. Alrighty. So what happens to r for values between 2 pi over 3 and 4 pi over 3? Well, we already mentioned that the values of r become negative, but we could have actually seen that by creating a sign chart. Remember, and we'll go through the whole process right here. We set 0 equal to this equation, and we already showed the work, so it's not worth showing again. We found two answers, 2 pi over 3 and 4 pi over 3. And we learned in the past, all the way back to Calc AB, that if you have found the place where a function, a continuous function, is 0, then this continuous function is only going to have one sign between, we'll say, 0 and 2 pi over 3, possibly a different sign, but maybe the same sign between 2 pi over 3 and 4 pi over 3, and then possibly a different sign, possibly the same from 4 pi over 3 to 2 pi. It can't change signs unless we get to a 0. And that's essentially our intermediate value theorem proving this. So let's create a quick sign chart. Okay, we're just going to go through and we're going to say, let's look at the signs of r, where r is 1 plus 2 cosine of theta, from 0 to 2 pi. And we have two zeros on here, right? We know r is 0 at 2 pi over 3, and we also know r is 0 at 4 pi over 3. And luckily, we already made a table, so this goes much faster. What's a value between 0 and 2 pi over 3? Well, looking at our unit circle, how about just pi over 2, right? Pi over 2 we did up here. We got 1. That is a positive. And then we saw that r was negative, and then at the end we saw r was positive. Okay, so moving on to part G, and then maybe jumping back to F here. Part G says, what theta values generate the inner loop, and why do they make the inner loop? Well, the values that make the inner loop are, of course, the negative ones. I'll draw a little arrow up here. So the negative R values. Spelling negative apparently is tough. There we go. The negative R values. Why do they make the inner loop? Because what happens is, with all the r values that are positive on these two intervals, r is going to stay in those little quadrants or in those zones. But because r is negative over here, nothing fills that spot. So instead of creating a loop over here, it creates the loop on the other side. It has to come back to 0 at some point too, because we start with a 0 and end with a 0, and it's a continuous function. Not a function, it's a continuous equation. So if it has to come back to 0, it's going to loop back in on itself. Does that always happen? Yes, it does. So what can we use that fact for to help us graph one of these without too much effort? Well, it's pretty easy. The first step is you solve the equation where you set r equals 0, and you're going to find two answers. Okay. The second step is you're going to make a quick sign chart. And you're making a sign chart. A lot of people will probably skip this step, but you're making a sign chart just to verify where those negative values are. It is possible for an interval to start with a negative somewhere else, but generally it's going to go positive, negative, positive, right? Once you've verified that those are negatives, then on 3, you're going to graph the equation, right? Now, to graph the equation, I do include a couple things. I do include 2 lines at the zeros, right? And I showed you that up above. I like to show these 2 lines here so that I can see where nothing should go. And the only other thing you're going to need is you're going to need the largest value of the inner loop and the largest value of the outer loop. So outer loop, largest value, and then the inner loop, largest value. How do we do that? Well, let's take a look at those values right now. You'll notice that the largest value of the outer loop, and we'll do this in green, is from the origin to 3. 3 is the largest value for the outer loop, and I'm just going to put this over here, is 3. The largest value of the inner loop from the origin to here is 1. And our equation, if you recall, was 1 plus 2 cosine of theta. How does that equation show us the value of the outer loop versus the inner? Well, it all has to do with cosine and sine. You should think, well, what's the largest value that cosine can ever be? And hopefully you're saying, ooh, it's 1. That's the largest cosine can ever be, and you're right. So when cosine is 1, which is the largest value, we're maximizing r. 1 plus 2 times 1 is 1 plus 2. Oh, look, that's 3. So can you just take a plus b, right? We talked about these as a and b and add them together. Yes, you can. No problem. All right, how do we get the inner loop then? Well, the inner loop, we think, what is the smallest value cosine can ever be? We're going to make the most negative r value. And of course, the smallest that cosine can ever be is negative 1. 1 minus 2 gets you negative 1, which converts to positive 1, because we said before, negative r values show up as positive r just somewhere else. How do we do that? We just do a minus b. Easy. So now we have a pretty darn quick way to determine a, where the inner loop occurs, right? That's these guys, and b, how large the inner and outer loops are. Once you have those, you can pretty quickly sketch in your graph. All right, last part of today before we get some practice problems in. They ask you to make a sine chart for dr d theta. Always good to bring in some calculus. We don't want to lose those skills. So we start with r. I'll leave a little gap here. 1 plus 2 cosine of theta. And we need to do d theta of each side. And it is always optional to show this step, but I think it's nice just so we remember how dr d theta was created, and we can see the with respect to part, right? I should have left off the plus because the derivative of cosine is negative 2 sine of theta. Don't need to multiply by the derivative of the inside because of the d theta. It's just 1. Okay, so simplifying a bit, dr d theta equals negative 2 sine of theta. Ooh, they're asking us to make a sine chart here. How exciting. We haven't done that in a while. To do that, we, of course, are going to set 0 equal to negative 2 sine of theta. I'll work sideways so we don't run out of room. Divide by negative 2. Where is sine of theta 0? And we're just going to look from 0 to 2 pi here. No reason to do any further because we complete a whole loop from 0 to 2 pi. So I think we end up getting, let's see, sine of 0 at 0, and then again at pi, and then if you'd like, again at 2 pi. Sine chart. Let's take a look at it. So we have this guy over here. We're going from 0 to 2 pi, and we're looking at the sines of dr d theta. Okay. We know there's really only one critical point. We don't call endpoints critical points, and 0 and 2 pi were critical points till they became the endpoints. We just have pi, which causes our derivative to be 0. And then I think we just need to test a few values, right? We need to look at our derivative and figure out what happens if we plug in something between 0 and pi. So why don't we think about using pi over 2? That's an easy value here, isn't it? Sine of pi over 2, which is negative 2 times 1. That's a negative value. And I bet you're going to guess what happens over here, and you'd be right. You end up getting a positive value. Well, what does that tell us then? Maybe we can see this a little bit more clearly looking at that Desmos graph again. It says from 0 to pi, we're negative, and then from pi to 2 pi, we are positive. So looking over here, we'll start back at the beginning. What's happening from 0 to pi? Well, at 0, a rotation of 0, we have a radius of 3. But as we start to move, this radius now is smaller than 3. Smaller than 3, smaller than 3, smaller than 3, smaller than 3. Now we're down to 1, right? Our radius is shrinking. And I'm still not at pi yet. At 2 pi over 3, we shrunk down to 0. And then what continues to happen? It actually continues to shrink. And you might say, well, wait, here's pi right now. You might say, well, wait, isn't the radius 1? But it's actually not. The radius is supposed to be over here. The radius is negative 1. So you could probably argue that the radius is decreasing until pi. And then what happens after that? Well, now our radius is getting bigger. And maybe now it's only negative 3/4, negative 1/2, negative 1/4, 0. Now the radius is going to be 1, and then maybe approximately 2, and then finally 3 again. So this is just telling us how large the radius is, or no, that's probably not right. It's telling us how the radius is changing as we change theta. But it's a little bit tricky here because although the radius does decrease, eventually the actual radius of the graph gets larger again because of the properties of polar graphs. All right, so we have a couple practice problems here. They should go pretty quickly, but I'd say maybe try, let's say, part 3, and then once you're done with part 3, unpause, see how you did, then same thing 4, and then same thing 5. So, ready, set, go. All right, so using algebra to determine how many times the graph goes through the origin. We've done this before. We set 0 equal to our equation. In fact, it is extremely similar to the one we just did. Subtract 2, divide by 4, we get negative 1/2. This is sine this time, so our values are going to be a little bit different, but hopefully we remember that pi over 6's make those negative 1/2, and sine is only negative in the 3rd and 4th quadrants. So I think we're going to need 7 pi over 6, that's the 3rd quadrant, and 11 pi over 6, that's the 4th quadrant. The graph touches the origin 2 times on that interval. On what interval of thetas are negative? Well, we already know where r is 0, so to figure out where r is negative, we just take our two, and it's not really right to call them critical points, we take our two values of theta that create, or that make r 0, and we make a sine chart out of it. 11 pi over 6 is really close to 2 pi, and we'll talk about how we can deal with that shortly too. 0 to 7 pi over 6, we could probably try pi. I think pi is right before there. And if we substitute pi in here, sine of pi is 0, so we just are left with 2. That's positive. 7 pi over 6 to 11 pi over 6. How about 3 pi over 2? 3 pi over 2 makes sine negative 1. 2 minus 4 is negative 2. And last but not least, from 11 pi over 6 to 2 pi, well, really what's happening is this sine chart goes on forever because there's no reason to actually stop our equation. We just arbitrarily chose to stop it at 2 pi. So you might think, well, where's the next time r becomes negative? Well, it's the next time we get coterminal with 7 pi over 6. So take a look down here. Here's 7 pi over 6. Here's 12 pi over 6. 13, 14, 15, 16, 17, 18, 19 pi over 6, I think, is our next one. So that means that our equation, the equation for r isn't going to change sign again until 19 pi over 6. So we can try any value, including 2 pi, to determine what the sign for r is in here. And I'm actually going to try 2 pi. Sine of 2 pi is 0. 2 plus 0 is 0. So this whole thing has a positive, which means this piece is positive right here. Nice. All right, what's the largest value of r which occurs, and what about the smallest? So if we're set up with r here, 2 plus 4 sine of theta, hopefully we can see that our largest is just adding our two, not really right to call them coefficients, but a and b values, is 6, and the smallest is going to be negative 2, which you could argue is 2, right? So let's go ahead and graph this. 7 pi over 6 and 11 pi over 6. Here's 7 pi over 6. Here's 11 pi over 6. This region in between those two is where r is negative. That's going to be left blank. We also know that this is a sine equation, which means it's going to really be around the positive part of the y-axis. Because of that, and we also know that the largest value is 6. 1, 2, 3, 4, 5. I didn't make a polar grid large enough, so that's awkward, but that's okay. And then we also know that the smallest is going to be negative 2, which would occur down here opposite of the largest, but because it's negative, we're going to go up here. At this point, it doesn't have to be perfect. We have enough to create our graph. This little loop, well, let's do the larger loop first, is going to look something like this. It always comes back to the origin somewhere, and then we're going to have an inner loop like so. And it's not going to be perfect. You could figure out where it crosses the axis if you'd like, but ultimately if you can get the general shape, you're just fine. All right, let's see how we did. I do have this pulled up on Desmos, and again, you're going to see it's not perfectly accurate, but it looks okay. Yeah, there we go, right? And it did go at about 2 right here. Maybe it'd be an interesting discovery to see if this value is always the same as the value of the inner loop. Was that true for this one over here? 1, 1, 1, it was, so that could possibly be true. I have not looked into it. It might be interesting to try. You could also see how this is created, right? We start over there, and we move out, and then we're back in right here, and now we create the inner loop, and then we finish from there. Excellent. All right. Second part, you again should try this, and then unpause when you're ready. Okay. Your goal here is to look at the different limaçons and or circles and decide what they look like and why they look like that. For example, and I'm actually going to come back to the circle at the end, though that is a circle. We can put that here. We know 1 plus 3 sine of theta. We know that a is less than b. Why is that important? Well, because sine can be negative 1, then we have 1 minus 3, which means r can become negative. And in this limaçon format, if r can ever become negative, then there's going to be an inner loop. So this is a limaçon with an inner loop. You could argue, well, it's because I learned that a is smaller than b. And you're right, but you do need to know why. And the why, again, is because you are able to make r negative. Same thing here, sine can become negative 1. 2 minus 3 is also going to be a limaçon with an inner loop. But here, a and b are the same, and sine can still become -1, but the smallest we ever get, 3 minus 3, is 0. So instead of hitting an inner loop, all that's going to happen is eventually our r is going to shrink to 0 and then start growing again. And don't graph this because it's not going to be perfect and you don't need to use this down here. This is why we're going to get that cardioid. It shrinks to 0 and instead of going on the inner loop, it starts getting positive again from there. So this is our cardioid, which is a type of limaçon, but no loops. And then when we have 4 plus 3 sine of theta, again, the smallest sine can be as -1. 4 minus 3 is still positive. So not only can this r never become negative, r can't even become 0. So r is always greater than 0, and so this is going to be a limaçon with no inner loop. Right, and these ones just kind of look like bulges over here, right? They just kind of go in like that, and sometimes they even bulge the other direction, kind of look something weird. Okay, and then last, very, very similar, 5 is much greater than 3. It'll never become negative or 0. So what about this circle one? Well, we get r is 0 plus 3 sine of theta, if you'd like. For this one, though, because there's a 0 in front, and sine can become both negative and positive, what's really happening here is half of this graph is going to be negative, half is going to be positive, and it ends up reflecting on itself to make a nice circle from the origin. Great. Last part. Graph the polar equation r equals theta by creating a table. Why does it look the way it does? Okay. You might remember that this graph is called easy for me to spell, Archimedes spiral. So it's a hint, it should be a spiral. So let's create this. Input, theta, output, r. Let's pick some easy ones. 0. When we input theta of 0, r is equal to whatever theta is, so that's also 0. 0, 0. Nice. Maybe we should just pick nice numbers. So let's go to, I guess it doesn't really matter, huh? It's going to be a little bit harder maybe to do this one because you're going to have to approximate our values of r. So let's do like pi over 2. So rotating to pi over 2 is right here. So our radius that we're going to go out is pi over 2. Think of pi as 3. 3 divided by 2 is 1.5. So a little bit bigger than 1.5, right? I think the math majors are cringing and the engineers are cheering. It's a common joke in the math world that engineers always approximate pi to 3. Just because it's easier to do math that way. So 3 over 2 is 1.5, so we rotate here and we go up 1.5-ish. Okay, so I've done something like this, and we've started to get a larger radius. Let's do pi next. And so pi is going to be about 3, so we're going to rotate over here, and now we're out to 1, 2, 3-ish, just a little bit bigger, and so it's going to be like that, right? And then if we do 3 pi over 2, okay, 3 pi over 2, and that was not great there. That should probably continue out. There we go, it's a little better. 3 pi over 2, 3 times 3 is 9. 9 divided by 2 is approximately 4.5. We're getting even worse as we go through, but 1, 2, 3, 4, 4.5, right? And then we have something like this, and we can start to see our spiral. That's going to get larger and larger and larger as we go out. Taking a peek at that really quickly, you can see that spiral right there. And you might have seen the spiral before in terms of golden ratios, and there's all sorts of interesting applications. And of course, we could keep going. I just stopped at 2 pi, which is approximately 6, right? 3 times 2 is approximately 6, a little bit bigger, but you get the idea. So thanks for hanging out with me today. As before, what's important for today, you need to know especially how to find the values that create the inner loop. There have been questions in the past that ask you to find just the area of the inner loop. And to do that, you need to know where the inner loop occurs. You should also be able to recognize which graphs have inner loops and which ones don't. And I'd say that's about it for today. So I'm excited to have you guys back tomorrow, where we're finally going to start the second part of calculus outside of the derivative, the area. How do we integrate and find the area of polar equations?